Space and time often appear solid and reliable. A room stretches from one wall to another. A road connects two points without interruption, and moments follow each other in a familiar order. Distances seem ever present. Time flows steadily, and everything appears divisible without end. This sense of continuity is far from faint. It is reinforced through every motion, every measurement, every memory. A table can be measured in meters, then centimeters, then millimeters. With more precise instruments, the same surface can be subdivided even further. Time behaves similarly. A minute divides into seconds, seconds into smaller intervals, and so on, in a process that seems never to reach a limit. It was this intuition that shaped the earliest scientific descriptions of the physical world. Classical geometry treated space as continuous. A line has length but no thickness. A point has position but no size, and between any 2 points another point can always be placed. These principles were not derived from experiment but from mathematical foundations, continuous, consistent, and in accord with observation. When physics began to describe motion and force, it adopted the same assumptions. By the late 17th century, Isaac Newton described space as absolute, existing independently of matter, a fixed stage for all moving objects. Time was also absolute, flowing uniformly everywhere. Events unfolded within this framework without altering it. Newton's laws of motion relied on this picture. Position, velocity, and acceleration are continuously determined. Forces act smoothly, producing continuous changes in motion. Mathematics allows positions and times to be known with arbitrary precision, at least in principle. This system proved extraordinarily effective. On human scales, classical mechanics predicts motion with near-perfect reliability. Bridges stand because stress is calculated accurately. Vehicles follow their trajectories because forces and motions obey predictable rules. Assumptions of continuous space and time introduce no detectable errors. The same held true for extraordinary experiences. Planetary orbits described by Newtonian gravity could be predicted centuries in advance. The positions of planets, moons, and comets follow smooth, continuous, stable paths. Even before modern instruments existed, astronomers calculated eclipses and interactions with astonishing accuracy. Distances on an astronomical scale reinforced the same conclusion. On average, Earth lies about 150 million km from the Sun. The nearest star beyond the Sun is more than 4 light-years away, roughly 40 trillion kilometers. These vast distances behave exactly as a continuous spatial framework would suggest. Yet, as measurement sharpened, a subtle truth emerged. On extremely small scales, the rules governing atoms and particles refused to cooperate with space-time geometry. Tools describing gravity cease to function smoothly. Distances become difficult to define. Time loses its steady beat, and the idea of a smoothly continuous universe gradually becomes an excellent approximation rather than absolute truth. Space and time can fluctuate, fragment, or only appear when observed from afar, like a calm sea hiding restless waves beneath. A quiet but profound question arises, not where space-time becomes strange, but when does space stop being classical and begin behaving like a quantum object? Light travels along paths that can be predicted with remarkable accuracy. Objects glide through space along smooth orbits, with no irregular structures obstructing the way. Time, when measured by the most precise atomic clocks, paints a similar picture. Quantum oscillations within atoms occur so steadily that the error amounts to less than a second over millions of years. Yet, even though the underlying mechanism is quantum, the time we experience and measure still flows continuously, showing no sign of leaping in discrete jumps at ordinary scales. Even when Einstein, in the early 20th century, overturned Newton's concept of absolute space and time and replaced it with a unified entity called spacetime, that continuity remained intact. In general relativity, gravity is no longer a force pulling across empty space. It is the manifestation of curvature that mass and energy impose on the very fabric of space-time. Spacetime remains a smooth geometric plane, describable continuously at every point, even though the curvature can become extreme near massive objects. Einstein's equations do not require a smallest unit of length or time. Everything continues to flow seamlessly, and observation has spectacularly confirmed this. We see light bending as it passes near the Sun, Mercury's orbit precessing precisely as predicted, time running slower in strong gravitational fields, and ripples in spacetime gravitational waves clearly detected by LIGO and other observatories. From laboratory experiments to distant cosmic scales, spacetime behaves like a smooth fabric, unwrinkled, unbroken. I often think that this smoothness is not accidental. It emerges because most of what we measure involves vast numbers of microscopic interactions. Any tiny irregularities, if they exist, are averaged out. Like a wooden table that seems solid, though in reality it is a lattice of atoms with enormous empty spaces in between. Or like temperature, we feel it rising and falling smoothly, though it is actually the average of billions of particle collisions. A river flows according to continuous fluid equations, even though at the molecular level, everything is discrete. Thus, smooth spacetime is likely only an effective description, extremely accurate at large scales, but possibly silent on deeper, far smaller structures. The reason we have never seen empty gaps in space, never sensed a moment of time skipping, is why both classical mechanics and relativity endure. They describe the world precisely as it appears to us. But physics does not stop at the familiar. As humans probe ever smaller distances and higher energies, the picture begins to change. Matter no longer moves along smooth paths. Energy appears in discrete packets. At extremely small scales, measurements reach fundamental limits. Quantum mechanics reveals that what we consider continuous at large scales is not an absolute feature of nature. When particles and fields obey quantum rules, a natural question arises. Is the spacetime in which they exist still continuous, or is that smoothness merely a limit of our observation? The classical model remains essential. It captures measurable behavior with astonishing precision. Any deeper description must reproduce this smoothness when applied, not to discard the familiar framework, but to understand why it works so well and where its limits lie. The idea that space and time might be more than a passive stage marks one of the greatest shifts in the history of physics. This turning point is closely associated with Albert Einstein, who, in the early 20th century, proposed a radically different approach to gravity and motion. Previously, gravity was seen as a force acting between masses in space. Objects attract one another, with strength depending on mass and distance. Space merely existed passively, providing distance and time for motion to occur. Einstein approached the problem differently. Instead of asking how objects move under gravity, he asked how space and time behave in the presence of matter and energy. The result was general relativity, published in 1915, built on a simple yet profound idea. Gravity is not a force in the traditional sense, but a geometric effect. Mass and energy alter the structure of spacetime, and objects move according to that structure. Spacetime is not merely an abstract backdrop, but a physical entity with properties that can change. To visualize this, set aside the complex mathematics. Spacetime can bend. This curvature affects how objects move. An object not acted upon follows the straightest possible path through spacetime. In flat spacetime, this path appears as uniform straight motion. In curved spacetime, the principle remains, but trajectories bend because the geometry is bent. This is why we can understand gravity without invoking a traditional force. A planet orbiting a star is not being pulled along a curved path by some invisible force. It is simply following the natural geometry of space-time, shaped by the star's mass. Its orbit is curved because space-time itself is curved. A common analogy: imagine a stretched fabric with a heavy object placed in the center. Smaller nearby objects roll toward the center not because they are pulled sideways, but because the surface beneath them slopes. Mass and energy determine the degree of curvature. Massive objects like stars and planets create stronger curvature. Extremely dense objects, such as neutron stars or black holes, produce extreme curvature, significantly altering the behavior of nearby spacetime. Light, although massless at rest, still follows a curved path near massive objects not because a force acts on it, but because spacetime itself is curved. One of the earliest famous confirmations of general relativity was gravitational lensing. In 1919, during a solar eclipse, astronomers observed that the apparent positions of stars near the Sun were slightly shifted, a clear demonstration that spacetime truly bends under the influence of mass. Light from stars, as it passes near the Sun on its way to Earth, is bent not by any pulling force, but by the curvature of spacetime around the sundial. This effect is small, but measurable, and matches Einstein's predictions exactly. Since then, gravitational lensing has become a standard observational tool in astronomy. Massive objects such as galaxies or clusters of galaxies bend light from more distant sources, producing arcs, rings, and multiple images of the same object. These observations confirm that the curvature of spacetime is not merely an abstract mathematical concept. It has direct consequences, observable by the naked eye and instruments alike. Time is also affected by curvature. In general relativity, clocks run at different rates depending on their position in a gravitational field. Clocks near a massive object run slower than those farther away. This phenomenon, called gravitational time dilation, has been verified through experiments placing atomic clocks at different altitudes. Even familiar systems like the Global Positioning System must account for it. Satellite clocks experience both special relativistic time dilation due to their speed and gravitational time dilation due to their distance from Earth. Without correction, positioning errors would accumulate rapidly. These confirmations establish that spacetime is an active participant in physical processes. It stretches, bends, and influences motion, not merely the stage on which events occur, but a determinant of how events unfold. Despite its dynamic role, spacetime in general relativity remains smooth and continuous. Curvature changes gradually from point to point. Distances and time intervals can be subdivided infinitely, and no minimum length exists. It behaves like a flexible but seamless fabric, and this smoothness underpins the functioning of general relativity. Mathematics assumes that spacetime has defined properties at every point. Curvature is described locally, meaning it can be determined in extremely small regions. The theory is based on the idea that spacetime can be probed at increasingly smaller scales while remaining meaningful. On the scales where general relativity has been tested, this assumption works remarkably well. From light bending near stars to the dynamics of galaxies, space-time behaves like a smooth geometric structure. Even gravitational waves, ripples in space-time generated by accelerating masses, confirm this picture. They propagate smoothly across vast distances, stretching and compressing space-time by minuscule amounts as they pass. The success of general relativity reinforces a previous idea. Smooth space-time is not naive speculation. It is a carefully tested description, valid across an astonishing range of conditions. At the same time, the theory hints at its limits. Certain solutions of Einstein's equations lead to singularities points where curvature becomes infinite, and the mathematical description breaks down. The centers of black holes are the most famous examples. These singularities cannot be observed directly, but their existence suggests that general relativity has been pushed beyond its domain of applicability. Infinite curvature is not a literal physical prediction, but a signal that the theory has reached its limit. These extreme regions arise when matter and energy are compressed into an extraordinarily small volume scales far removed from everyday experience. This hints at the possibility that space-time behaves differently under extreme conditions. Yet it is important to emphasize what general relativity does correctly. It provides a coherent predictive framework in which spacetime is both smooth and dynamic. It explains gravity without invoking a force acting across empty space, unifies space and time into a structure that responds to matter and energy, and deepens the notion of smooth spacetime rather than diminishing it. Space and time do not merely flow continuously. They have structure, geometry, and actively participate in the physical world around us. Every curve, every deformation, every oscillation in spacetime carries energy and information. As we begin to probe deeper, difficult questions arise. Does this smooth geometry hold at all scales? Or under sufficiently fine scrutiny must space-time be described by entirely different principles? What matters immediately is the proven truth. General relativity transforms space-time from a silent backdrop into a dynamic, measurable entity, smooth, continuous, and predictable. This success must be fully appreciated before we even consider going beyond it. It is one of the most successful theories humanity has ever developed, continuously tested over decades and across countless environments, from Earth-bound laboratories to the observable edge of the universe. Wherever the theory is applied within its intended domain, it works with astonishing precision. At large scales, general relativity describes gravity as the curvature of spacetime caused by mass and energy. This description not only explains planetary motion and galactic structure, but also captures the expansion of the universe. Observations of planetary orbits, binary star systems, and galactic dynamics align closely with Einstein's equations. One of the clearest confirmations is gravitational waves, ripples in spacetime emitted by accelerating masses, particularly in violent cosmic events. In recent years, detectors like LIGO have observed gravitational waves produced by merging black holes and neutron stars. The observed signals match the predicted waveforms astonishingly well. Timing, amplitude, and decay all correspond to the theory. This demonstrates that space-time behaves exactly as general relativity describes, even under the most extreme conditions. General relativity also excels in strong gravitational fields. Neutron stars, among the densest objects in the universe, contain masses exceeding the Sun's, yet are compressed into spheres only about 20 kilometers wide. The gravitational field at their surfaces is billions of times stronger than Earth's. Nevertheless, general relativity accurately describes the structure, stability, and gravitational influence of these stars. Black holes, an even more extreme challenge, form when massive stars collapse under their own gravity, compressing matter to the point that not even light can escape. Today, the existence of black holes is no longer theoretical. It is confirmed through multiple lines of evidence. From the motion of stars around galactic centers, high-energy radiation from accretion disks, to direct imaging of black hole shadows. The mathematical description of black holes in general relativity originates from Schwarzschild's 1916 solution, which precisely describes spacetime around a non-rotating spherical mass. This solution reveals the event horizon, the boundary beyond which light cannot escape, and a singularity at the center. At the event horizon, spacetime curvature becomes extremely strong, but still finite. An observer falling past this boundary would not immediately notice anything unusual. From their perspective, physics continues to unfold smoothly and continuously, exactly as general relativity predicts. At least initially, in all cases, from the gentle ripples of space-time to the most extreme objects, general relativity remains robust, serving both as a firm foundation for modern science and as a gateway to deeper questions about the very nature of space and time. From the perspective of a distant observer, time appears to slow dramatically as one approaches the event horizon of a black hole. This effect has been confirmed indirectly through observations of matter spiraling into black holes, as well as through gravitational wave signals from black hole mergers. Up to this point, general relativity remains robust, both theoretically consistent and observationally successful. However, the problem arises when we look straight toward the central singularity. A singularity is a point where physical quantities, such as space-time curvature, become infinite. In the Schwarzschild solution, the singularity lies at the center of the black hole, where the equations predict density and curvature diverging to infinity. Similar points also appear in models of the early universe, when the equations are extrapolated backward in time, leading to a state of extremely high density often associated with the moment of the universe's initial expansion. These infinite values are not merely large numbers. They signal the breakdown of the mathematical framework. Physical quantities lose meaning, distances collapse to zero, and time ceases to flow in any well-defined manner. The theory no longer provides reasonable predictions. Importantly, singularities are not physical objects like planets or stars. They should be understood as warning signs, indicating that the foundational assumptions of the theory are being pushed beyond their domain of validity. More specifically, singularities remind us that treating spacetime as a smooth, continuous geometry may no longer be accurate under extreme conditions. This is a crucial distinction. General relativity does not gradually fail as conditions become harsh. It remains accurate right up to the edge of singular regions. Only when curvature and density reach extreme levels does the description break down. This does not mean the theory is wrong, but rather incomplete. This incompleteness becomes even clearer when quantum effects are considered. Neutron stars and black holes compress matter into extremely small volumes. At sufficiently high densities, the quantum properties of matter cannot be ignored. Electrons, neutrons, and other particles follow quantum rules, limiting how closely they can be packed together. These effects, such as neutron degeneracy pressure, prevent many stars from continuing to collapse. General relativity, by contrast, treats matter largely classically. It does not incorporate the quantum behavior of particles at a fundamental level. This is not problematic at low densities or large scales, but it becomes critical when matter is compressed into extreme states. The same issue applies to space-time itself. The theory assumes that space-time can be described as smoothly continuous down to arbitrarily small scales, while quantum mechanics imposes fundamental limits on measurement and precision. When energy is concentrated into extremely small regions, quantum fluctuations become significant. Attempting to probe space-time at such tiny scales requires high energies, which in turn strongly disturb the very space-time being measured. This tension suggests that singularities arise not because space-time truly becomes infinite or ill-defined, but because the theory is being applied beyond its valid regime. Smooth geometry works perfectly well until one enters regimes where quantum effects cannot be ignored. Signs of this limitation also appear in cosmology. Applying the relativistic equations to the entire universe describes an expanding space-time, denser and hotter in the past. Extrapolating this expansion backward leads to a state of extremely high density and temperature, ultimately predicting an initial singularity. However, extrapolating the history of the universe assumes that classical space-time remains valid all the way back to the very beginning. When the universe was extremely small and contained enormous energy, quantum effects were unavoidable. The appearance of a singularity in this context once again highlights the boundary where the classical description breaks down. It is important to emphasize that these issues do not undermine the success of general relativity. The theory remains the best description of gravity and spacetime on macroscopic scales, and its predictions continue to be confirmed with increasing precision. The problem arises only when the theory is extended into regimes it was never designed to handle. In this context, singularities become valuable. They indicate points where new physics must emerge, places where a more complete framework must take over. Combining both the geometric perspective of general relativity and the probabilistic structure of quantum mechanics, the existence of these limits provides motivation for seeking a deeper theory. It is not because general relativity fails, but because it succeeds so completely within a well-defined domain. Understanding where and why the theory ceases to operate offers clues about the fundamental structure of spacetime itself. The emerging picture is one of layered description. The smooth geometry of spacetime governs behavior on the large scales of the universe. It explains gravity, motion, and cosmic structure with high precision. But at extreme densities and very small scales, foundational assumptions may no longer hold. Recognizing both the successes and limitations of general relativity lays the groundwork for the next step. If smooth geometry breaks down only under the most extreme conditions, the question becomes more specific and less speculative. At what scale do these conditions appear? And what replaces the classical description when they do? Cracks in smooth spacetime do not appear everywhere. They emerge only when nature is pushed to its limits. This focus narrows the problem and guides further exploration. When the limits of classical space-time become clear, an entirely different framework emerges. This framework was not developed to explain gravity or cosmic structure, but to understand nature at very small scales: quantum mechanics. It describes a world that is neither smooth nor continuous, as classical physics assumed. Quantum mechanics emerged in the early 20th century, not from philosophical speculation, but from empirical failure. Classical physics could not explain how atoms emit light, how energy is exchanged, or why matter is stable. Its predictions failed to match repeated observations. Something fundamental was missing. The first clues arose from the study of heat and radiation. When physicists observed glowing hot objects, classical theory predicted that energy should be emitted continuously across all frequencies. This prediction conflicted with reality, sometimes implying infinite energy. The problem was not subtle. The simple equations simply did not work. In 1900, Max Planck proposed a bold solution. Energy is not exchanged continuously, but in discrete packets, dependent on frequency and defined by a fundamental constant. According to this proposal, energy arrives in quanta rather than flowing continuously. The initial idea of quantization was merely a mathematical fix. Planck himself was cautious about its meaning, yet the results perfectly matched experimental data. What initially seemed a technical adjustment turned out to reflect a profound feature of nature. In the following decades, the principle appeared repeatedly. Albert Einstein applied it to explain the photoelectric effect, demonstrating that light behaves as discrete units of energy. Niels Bohr used quantization to describe atomic structure, proposing that electrons occupy defined energy levels rather than moving freely. Atoms do not absorb or emit energy arbitrarily. Instead, they take in or release energy in discrete, well-defined levels. While classical mechanics imagines a particle can possess any energy and glide through space along a smooth trajectory, the quantum world imposes surprising limits. Each energy jump occurs suddenly, without a continuous transition. But this does not imply that all matter is composed of simple, indivisible blocks. It merely reflects how the system operates and what can be measured. Quantum mechanics does not predict absolute outcomes, but only probabilities. It tells us the likelihood that a particle will be in a given state, not a single, determined position. From these probabilities, Werner Heisenberg showed that it is impossible to know both the position and momentum of a particle with absolute precision. The more precisely one is known, the less precisely the other can be determined. This is not a limitation of measurement tools. It is a fundamental feature of nature. At microscopic scales, the notion of a smooth trajectory loses meaning. A particle does not exist along a specific path, but rather spreads across a distribution of possible positions and momenta. Only when these distributions are sufficiently narrow does classical mechanics emerge as a stable illusion. Probability replaces certainty, not to weaken theory, but to provide an accurate description of nature. Quantum predictions are often astonishingly precise. The difference is that they are expressed as probabilities, governed by well-defined mathematical rules. The role of measurement in this world is also transformed. The values of position, energy, or spin are determined only when we measure them. Interference experiments with electrons or atoms, discrete energy spectra all confirm that particles behave as probability waves. These principles are not merely theoretical. They form the foundation for lasers, semiconductors, atomic clocks, technologies that operate as precisely as theory predicts. At small scales, ignoring quantum mechanics is impossible. Electrons, photons, and atoms do not obey classical logic. They possess discrete energy, behave probabilistically, and any attempt to apply classical trajectories leads to contradictions. When gravity and spacetime are considered, these limits become even more significant. Conversely, at large scales, quantum effects average out, producing the stable reality we are familiar with. Classical mechanics emerges as a consequence of the underlying probabilistic micro-world. In this light, the gap between classical and quantum is not a minor detail. It is a fundamental difference in how physics defines and measures reality. General relativity portrays spacetime as a smooth, continuous, and deterministic fabric. Every curve, every motion follows strict laws, as if the universe were woven with perfect rhythm. In contrast, quantum mechanics describes matter and energy as discrete, governed by probabilities, with uncertainty always present. Both theories are experimentally verified and operate flawlessly within their respective domains. The problem arises when we attempt to combine these two theoretical frameworks. Quantum mechanics assumes a fixed spacetime in which particles and fields exist and evolve. General relativity, on the other hand, treats spacetime as a dynamic entity, curved by energy and mass. At large scales, when gravity is weak, this conflict seems negligible. Quantum effects can be ignored, and spacetime behaves classically. When quantum effects dominate but gravity remains weak, spacetime can still be treated as a fixed background. However, when both gravity and quantum effects are strong simultaneously, the familiar assumptions of both theories fail. This occurs in extremely small regions where matter and energy are compressed into tiny volumes near cosmic singularities or at scales far beyond current experimental reach. Here, classical spacetime and standard quantum mechanics cannot be applied directly. The emergence of quantized behavior marks a fundamental turning point. It does not merely add details to the old framework, but changes how physical quantities are defined and related. The question, when does spacetime become quantum, is not about replacing one theory with another. It is a challenge of limits where the assumptions of each theory no longer hold, and how they might be reconciled. The quantum world does not negate the successes of classical descriptions. It explains why they work so well on large scales. At the same time, it sets a clear boundary. Beyond it, continuity, determinism, and smooth geometry are no longer guaranteed. One theory is based on smooth spacetime, the other on discreteness and uncertainty. The intersection of these two descriptions is where the problem of quantum spacetime becomes unavoidable. When general relativity is placed alongside quantum mechanics, a profound issue arises. Each theory is perfectly successful within its own domain, but their assumptions cannot be merged into a single description. The difference is not merely experimental. It lies deep in how each theory understands reality, particularly in how they treat spacetime. In quantum mechanics, spacetime is a fixed background. Particles exist within it. Their positions and properties change over time, but the underlying structure is unaffected. This is background dependence, and it works perfectly when gravity is weak or spacetime curvature is small. General relativity is the opposite. Spacetime is dynamic, with no fixed background. Its geometry is determined by the distribution of mass and energy. Matter tells spacetime how to curve, and spacetime tells matter how to move. Geometry and dynamics become inseparable. This difference alone creates conflict. Quantum mechanics requires a stable background for probabilities to evolve. General relativity denies the existence of that fixed background. When spacetime itself changes, the fundamental structure required by quantum theory becomes unstable. This tension becomes even more acute when attempting to apply quantum methods to gravity. In quantum mechanics, forces are described through quantum fields. These fields oscillate continuously, exchanging energy in discrete amounts. When calculating, physicists sum over all possible interactions, each contributing to the final probability of a given outcome. This approach has proven remarkably successful for electromagnetic and nuclear forces. However, applying the same approach to gravity reveals a fundamental difference. Gravity is not merely a force, it is directly related to the curvature of space-time. To quantize gravity, One might attempt to treat small fluctuations in spacetime geometry as quantum particles. In theory, this seems reasonable. In practice, the calculations produce infinite values at virtually every step, rendering measurable physical quantities meaningless. Unlike other quantum theories, where infinities can be tamed through renormalization, quantum gravity does not cooperate. New infinities appear at every level of approximation. No finite set of parameters can absorb them, and predictability is lost. This is not merely a technical issue, it reflects a deep conceptual difference. Quantum mechanics assumes that physical quantities exist within spacetime, whereas general relativity treats spacetime itself as a physical entity. A vicious cycle emerges. To probe spacetime at extremely small scales, high energy is required. Yet this energy strongly curves spacetime, making its structure increasingly indeterminate. The more precisely one attempts to observe the geometry, the less well-defined it becomes, and the mathematical expressions reflect this instability through divergences. This situation differs markedly from other quantum theories, where infinities can be controlled and predictions remain viable. The problem extends further. If spacetime becomes quantum, distances and time fluctuate, and the notion of a well-defined spacetime geometry is lost. Quantum mechanics, however, relies on a precise concept of time to describe the evolution of probabilities. The state of a system is compared across different moments. If time itself becomes uncertain, the foundational framework of quantum theory begins to collapse. Additionally, the two theories conflict over locality. Quantum field theories assume interactions occur at well-defined points in space-time. General relativity allows space-time to be curved, removing the notion of global simultaneity. There is no universal time to divide the universe into synchronized moments, making it challenging to define a uniformly evolving quantum state. Despite all these difficulties, it is important to emphasize one point. There is no experimental contradiction between quantum mechanics and general relativity within the domains where both have been tested. Each theory continues to operate excellently in its own regime. But when one tries to apply them simultaneously, theoretical conflicts become evident, revealing profound limits to our understanding of space-time and matter. The problem only arises when both quantum effects and strong gravity are present simultaneously. In most laboratory experiments, gravity is weak enough to be negligible. In most astronomical contexts, quantum fluctuations average out and nearly vanish. This separation of scales allows the two theories to coexist without conflict. The real difficulty emerges when we push to extreme scales, near black hole singularities, in the earliest moments of cosmic expansion, or when attempting to describe space-time at distances smaller than any current experiment can access. In these regions, no theory can be applied directly without modification. General relativity predicts that space-time curvature becomes infinite. Quantum mechanics predicts unavoidable fluctuations. Each theory signals that its assumptions are being violated. This is why the question of quantum space-time remains unresolved. The reason is not a lack of effort or imagination. It stems from the foundational principles of the two most successful physical theories pulling in different directions. One treats space-time as smooth and deterministic. The other treats physical quantities as probabilistic and discrete. When space-time itself is included among these quantities, the mathematical structure and concepts become unstable. This instability leads to an important conclusion. It is not a matter of one theory being right or wrong, both are correct within their domains. The issue is that neither theory is complete. Resolving this conflict may require a new theoretical framework, one that reduces to general relativity at large scales and to quantum mechanics at small scales. This framework must explain why smooth space-time emerges from a deeper description and why quantum effects become negligible under normal conditions. Until such a framework emerges, the conflict is not a failure, but a guide. It marks the boundary between what is understood and what is not. When successful physical theories collide, the cause is often not location, material, or environment, but scale. An object can behave completely differently depending on the scale at which it is observed. Physics does not provide a single description valid for all distances and energies. Instead, it produces layers of description, each appropriate for a specific scale. This idea is familiar even outside physics. From a high vantage point, a coastline appears smooth. Up close, it becomes jagged. At the scale of individual grains of sand, the concept of a straight line loses meaning. Physical laws operate similarly. At human scales, objects obey classical mechanics. Motion is continuous, forces create smooth acceleration, and spacetime is stable. These assumptions work because the scale is large compared to the microscopic structure of matter and energy. At the atomic scale, the picture changes. Electrons do not orbit the nucleus like tiny planets. Energy levels become discrete, and probability replaces trajectories. Quantum mechanics becomes essential, not because classical mechanics is wrong, but because it averages over details that are now important. At even larger scales, stars, galaxies, the universe, gravity dominates. General relativity is the appropriate description. Space-time curvature determines motion, and time flows slower or faster depending on gravitational conditions. Quantum effects still exist, but are typically negligible due to averaging over vast numbers of particles. Each description is accurate within its domain. Problems arise only when a description is pushed beyond the scale where its assumptions hold. From this perspective, the question of quantum spacetime becomes clear. The issue is not where, but at what scale. When smooth geometric descriptions are no longer sufficient, quantum mechanics and gravity converge. Physics has long recognized and developed a method to manage scale: effective theories. An effective theory describes phenomena at a given scale without attempting to capture all fundamental details, because those details do not significantly affect observable behavior. Classical mechanics, with all its simplicity, remains a powerful tool. It ignores atomic structure and disregards quantum uncertainty, yet it still accurately predicts the motion of vehicles on roads, planets orbiting the sun, or spacecraft gliding through vast space. Similarly, fluid dynamics treats liquids as continuous substances, even though each drop of water is composed of countless discrete molecules. The success of these theories does not lie in describing every particle in detail, but in the fact that small-scale details average out when observed at larger scales. Smooth space-time may operate under the same principle. When observed and measured, it appears as a continuous geometric structure with gradually varying curvature, and all distances and times can be measured accurately. The mathematics of general relativity works effectively, not because space-time is fundamentally perfect, but because this smooth description captures the dominant behavior at scales we can access. If a fundamental structure of space-time exists at extremely small distances, it may be entirely unrelated to most familiar physical phenomena. Just as a particle does not alter a planet's orbit, the granularity of space-time does not affect everyday experience. This idea is connected to renormalization, a set of techniques in quantum field theory used to explain how physical behavior changes with scale. Renormalization formalizes the notion that each resolution carries its own description. As one moves from small scales to large, some details fade while others dominate. Within this framework, mass, charge, or interaction strength are no longer absolute constants, but scale-dependent. Physical laws remain intact, but the way they manifest changes with scale. What is important at one level may become negligible at another. Applied to space-time, this opens a possibility. The smooth geometry of general relativity may emerge from a more complex structure when viewed at large scales. At smaller scales, new degrees of freedom appear, shaping how space-time behaves. Emergent phenomena are not speculative ideas. Temperature arises from molecular motion, pressure from particle collisions, elasticity from atomic bonds. No single particle possesses these properties, yet they become real and measurable at macroscopic scales. Smooth space-time may be similar. It need not be a fundamental property. It could simply be a characteristic that appears when microscopic details are averaged. From this perspective, we understand why general relativity works. Not because space-time is smooth at all scales, but because the smooth description correctly reflects the physics at the scales we can measure. The accuracy of the theory also explains why problems arise only under extreme conditions. Singularities, such as black holes, appear when matter and energy are compressed into extremely small volumes. Quantum fluctuations become significant as distances shrink. These are precisely the situations where scale matters most, and where effective descriptions can fail. Viewed in this way, the conflict between quantum mechanics and general relativity is no longer mysterious. Each theory is an effective description, valid at a particular scale. Quantum mechanics governs small systems, where fluctuations and randomness dominate. General relativity governs large systems, where geometry plays the leading role. Difficulties arise in the narrow overlap, where both effects are important. Near black hole singularities, in the earliest moments of the universe, or in any attempt to probe space-time at extremely small distances. In these regions, classical geometry or standard quantum theory cannot be applied straightforwardly. The key factor is scale, not location. A region of space may appear smooth at one resolution but reveal structure at another. A table looks solid from afar, but under a microscope, it reveals a lattice of molecules and the empty space between atoms. The nature of the object does not change, only its description does. Space-time may behave similarly. If its quantum properties appear only at scales far smaller than current measurement capabilities, it does not conflict with everyday experience or astronomical observations. It simply lies beyond the resolution of existing instruments. The problem is not diminished, it becomes clarified. Instead of asking where space-time changes, we focus on the smallest scale at which the smooth description fails. Recognizing scale as the crucial variable allows us to pose precise and quantitative questions, leading to a deeper understanding of the nature of space-time. The concept of a fundamental limit begins to take shape when we realize that there may exist a smallest physically meaningful length or time. This limit defines the scale at which the effective smoothness of space-time ends. But searching for this scale is not about finding a hidden boundary in space. It is an effort to determine the point at which our current description must give way to a deeper form. When attention turns to extremely small scales, a particular length naturally emerges in theoretical physics, the Planck length. It does not come from direct measurement, but is constructed from the fundamental constants that govern nature. The Planck length lies at the center of every discussion about quantum spacetime. Its name is associated with Max Planck, who at the beginning of the 20th century proposed natural units. Planck was concerned with defining quantities that do not depend on human measures such as meters or seconds, but derive directly from the structure of physical laws. To construct these units, he combined constants that appear in both quantum mechanics and gravity. A constant setting, the scale of quantum effects, a constant determining the strength of gravity, and a constant linking space-time via the speed of light. When combined in a particular way, the result is an extremely small length scale. This length is unimaginably tiny, about 1.616 times 10 to the power of negative 35 meters. For comparison, an atom is roughly 1 times 10 to the power of negative 10 meters wide. A proton is about 1,000 times smaller than an atom. The Planck length is many orders of magnitude smaller still. Indeed, the number of Planck lengths in a proton is comparable to the number of protons in the observable universe. Despite its minuteness, the Planck length is not arbitrary. It marks the scale at which quantum mechanics and gravity become equally important. At larger distances, gravity governs the macroscopic structure, while quantum effects average out at atomic scales. At the Planck scale, any attempt to concentrate energy to probe smaller distances triggers strong gravitational effect. This is not a technological limit, but a necessary consequence of physical laws. To measure a small distance, one requires a probe with a short wavelength. A short wavelength implies high energy. As energy increases, the probe's gravitational impact also increases. At sufficiently high energy, concentrating energy into a small region causes spacetime to react violently. Increasing energy beyond this limit does not improve resolution, but instead distorts the measured region. If energy is confined to a sufficiently small volume, the result is the formation of a black hole. At this point, information about smaller distances becomes inaccessible. Here, the Planck length emerges as the scale marking the transition. Below this scale, the act of measurement itself disrupts space-time to the extent that the concept of distance loses practical meaning. It is no longer clear what it means to say that two points are a certain distance apart. Therefore, the Planck length is often described as the smallest measurable length. However, this does not imply that space-time is composed of discrete chunks of Planck size. It merely indicates that ordinary procedures for defining and measuring distances cease to function. In physics, operational meaning is essential. A quantity is considered physical only if there exists, at least in principle, a way to measure it. If no experiment can distinguish between two values, the difference may not correspond to physical reality. At distances smaller than the Planck length, no measurement procedure can probe the structure without using energy that destroys the very geometry of space-time. This implies that speaking of smaller distances may no longer have physical meaning, even though mathematical descriptions can still be written. This idea changes the perspective. Classical geometry assumes that distances can always be subdivided. Quantum mechanics challenges this assumption with uncertainty. Gravity further intensifies the challenge by making space-time dynamic and sensitive to energy. Combined, they imply a fundamental limit. It is important to be precise about this limit. The Planck length is not a boundary that has been directly observed. No experiment has directly probed distances near this scale. It is a theoretical construct, inferred from well-established constants. Its significance lies in consistency. If quantum mechanics and general relativity are valid in their respective domains, then there must exist a scale at which neither can be applied independently. The Planck length defines that scale, and therefore it continuously appears in discussions of quantum gravity. At the Planck length, space-time still behaves approximately continuously and can be approximated by a smooth description. Below it, the assumption of continuity is no longer guaranteed. The theory does not specify the alternative form of geometry, only that infinite smoothness cannot be assumed. Some theoretical approaches suggest that space-time may become discrete at this scale, with area and volume taking quantized values. Some physicists have proposed that space-time may have a fundamentally relational nature, with geometry emerging from deeper underlying interactions. Others go even further, suggesting that space-time may not be fundamental at all. But all approaches agree on one point: the Planck length marks the limit of the classical concept of distance. Another way to view this is through dimensional analysis. The constants used to define the Planck length are not chosen arbitrarily. One constant governs quantum uncertainty, another determines the strength of gravity, and a third relates space to time. Any attempt to describe space-time at the smallest scale must involve all three. This is what makes the Planck length a natural scale, not a human invention. It is not introduced to fix a calculation. It emerges from the structure of the theories themselves. This also explains why smaller lengths do not appear naturally in existing physics. There is no mechanism to probe space-time below this scale in a meaningful way. Every attempt encounters the same fundamental obstacle. Concentrating energy leads to gravitational collapse. The Planck length, therefore, serves as a conceptual boundary. It does not tell us what space-time is made of, but only indicates the point at which our current description ceases to be meaningful. This boundary does not imply absolute certainty. Physics has previously encountered limits that seemed insurmountable, only to be later reinterpreted. What makes the Planck length different is that it emerges from the combination of well-tested theories, not from missing data. Caution is required. The Planck length is a guideline, not a direct measurement. It indicates where new physics is needed, but does not specify what that physics looks like. What can be stated with confidence is that if space-time truly becomes quantum, this occurs at or near the Planck scale. At this scale, quantum uncertainty, gravitational interaction, and space-time structure converge. Above this scale, smooth geometry still functions well. Below it, the concept of distance becomes unstable, and the language of points, lengths, and distances begins to lose its physical foundation. The Planck length becomes a milestone in the discussion. It defines the scale at which questions about quantum space-time are no longer speculative, but unavoidable. The next step is to understand why measurement fails completely at this scale, and what that failure reveals about the nature of space-time. Time is often considered the most reliable element in physical description. Events occur, time flows, and cause and effect sequences seem fixed. Even when space is curved or distorted, time provides a continuous sequence in which physics unfolds. Classical mechanics relies on this assumption, and even general relativity, with all its flexibility, preserves the concept of continuous duration. If distance can encounter a limit where the notion of length loses operational meaning, there is reason to ask whether time faces a similar limit. The temporal equivalent of the Planck length is the Planck time, defined as the time it takes light to travel one Planck length in vacuum. Like the Planck length, it is constructed from constants governing quantum mechanics, gravity, and relativity. It does not arise from experiment, but from consistency between well-tested theories. Numerically, the Planck time is about 10 to the power of -43 seconds, not only minuscule by human standards, but smaller than any time interval that could be measured, created, or resolved by any known physical process. Its significance lies not in the absolute value, but in what it represents. In everyday physics, time intervals can be shortened with faster clocks or higher energy processes. Atomic clocks measure time based on oscillations within atoms, achieving extraordinary precision. Particle physics experiments probe interactions occurring over extremely short durations. In all these cases, time behaves as a continuous parameter, divisible as technology advances. Quantum mechanics complicates this picture by linking time and energy. Processes occurring over extremely short intervals are accompanied by large energy uncertainties. This is not a limitation of instruments, but a fundamental feature of quantum systems. Shorter time intervals require higher energies to be measured meaningfully. The difficulty becomes critical when gravity is included, because high energy deforms space-time. This is not a mere side effect. It is a central intuition of general relativity. Energy and momentum determine how space-time curves. Attempting to probe a time interval comparable to the Planck time requires such enormous energy that it strongly affects the geometry of space-time itself. At this point, the concept of a well-defined time interval begins to fail. As with distance, the act of measurement disrupts itself. The physical processes used to define a time interval alter the structure of space-time where that interval is being defined. The idea of a clear separation between one moment and the next becomes unstable. This instability directly impacts causality. Since causality relies on the ordering of events, an event causes another if it occurs earlier in time and can influence it through physical processes. General relativity refines this notion by linking causal structure to space-time geometry. Light cones determine which events can affect others. Even in curved space-time, causal order remains well-defined. At extremely small timescales, this structure becomes precarious. If space-time itself fluctuates due to quantum effects, the light cones defining causal relations also fluctuate. The clear distinction between before and after may blur. This does not mean causality disappears in the usual sense. Rather, the classical concept of precisely ordered intervals no longer applies at the smallest scales. Cause and effect still exist, but are no longer represented clearly on a classical time axis. This issue becomes especially important when considering the early universe. Cosmological models based on general relativity describe an expanding universe, which was denser and hotter in the past. Tracing the expansion backward, time intervals shrink and energy density increases. Ultimately, the equations predict a state of extreme density at the beginning of expansion. Near this point, Typically associated with the universe's first moments, time intervals reach the Planck scale. In this environment, classical spacetime cannot exist in its usual form. Quantum fluctuations in geometry are unavoidable. This does not imply that the universe began at a definite moment in the classical sense. It means that the concept of time may not extend meaningfully beyond a certain point. Asking what occurs before that point is like asking what lies north of the North Pole, a question that presumes a structure that may no longer exist. Importantly, the Planck time should not be understood as the smallest tick of a cosmic clock. There is no evidence that time progresses in discrete steps of this interval. Many approaches to quantum gravity do not predict time quantization in such a simple way. Instead, the Planck time marks the limit of classical description. It defines the scale at which treating time as a smooth, continuous parameter is no longer guaranteed. At this scale, time still behaves in a way consistent with experience and experiment. Clocks can be synchronized, intervals can be compared, and causality is maintained. Below this scale, the foundational assumptions of these concepts are no longer secure. This mirrors the situation with distance. The Planck length does not prove that space is made of indivisible units. It merely indicates that the operational concept of distance loses meaning below a certain scale. Similarly with time, like space, time may be emergent. It may arise from deeper processes and only approximate continuity at large scales. At extremely small scales, the language of moments and intervals may not correspond to any physical entity. This perspective helps explain why time works so well in classical and relativistic physics. It is not because time is fundamental at all scales, but because it is an effective concept, valid where quantum fluctuations are negligible and geometry is stable. Recognizing the limits of classical duration does not undermine physics. On the contrary, it clarifies its domain of applicability. It explains why any attempt to describe the early universe or the interior of black holes encounters a conceptual breakdown rather than smooth interpolation. The Planck time thus becomes a landmark, signaling where familiar concepts of time reach the boundary of usefulness. Beyond that boundary, new descriptions are required not because time disappears, but because classical ideas of duration no longer apply. Together with the Planck length, it reinforces a coherent picture. Smooth, space-time, with continuous distances and times, is an excellent description at accessible scales. But at extremely small scales, both space and time may require a different foundation. The breakdown of continuity is not an exception. It is a clue, pointing toward a deeper structure, in which space-time, as we usually understand it, only emerges when viewed from sufficiently far away. At extremely small scales, the notion of an empty, featureless vacuum ceases to hold. What appears as emptiness in classical physics becomes dynamic in quantum mechanics. Even when no particles are present, space is not truly empty. It is filled with fluctuations arising from the fundamental structure of quantum mechanics, known as vacuum fluctuations. In quantum mechanics, fields exist everywhere, even in the absence of particles. Each field possesses a minimum energy called zero-point energy, which cannot be eliminated. It is not related to motion, heat, or radiation in the usual sense, but arises from the inherent uncertainty of the quantum system. A quantum field cannot be completely static, just as a particle cannot have both its position and momentum precisely defined. As a result, even the lowest energy state includes fluctuations. These fluctuations are not mere mathematical formalities, they have observable consequences. For example, the Casimir effect. Two uncharged metal plates placed close together experience a measurable force due to the modification of the quantum vacuum between them, or spontaneous emission of light from excited atoms, which occurs because the vacuum is not static. In most contexts, these effects are extremely small. They average out and hardly affect behavior at macroscopic scales. But when gravity is considered, the situation changes. General relativity teaches that energy affects the geometry of space-time. Every form of energy, including zero-point energy, contributes to curvature. If quantum fields fluctuate, the associated energy fluctuates. If energy fluctuates, space-time geometry must respond. This opens a remarkable possibility. At extremely small scales, space-time itself may fluctuate. Instead of being a smooth geometric structure, space-time could undergo rapid and continuous variations in curvature. Distances and angles are no longer fixed. They shift and blur under the influence of fundamental quantum effects. The classical picture of a stable backdrop no longer holds. This idea was explored in detail by John Wheeler. He realized that if quantum mechanics applies to everything, it must also apply to space-time itself. Wheeler proposed that at extremely small scales, space-time could be completely indeterminate, a concept he called quantum foam. The term is metaphorical but emphasizes an important point. Like bubbles of water forming, merging, and breaking apart, quantum space-time could continuously create and destroy geometric features. Tiny distortions, tunnels, or oscillations appear and disappear over extremely short intervals. It is important to clarify, quantum foam is not a verified physical description. It is a conceptual image intended to capture the idea that space-time may not be smooth when observed closely. The details depend on the correct theory of quantum gravity, which has yet to be established. Nevertheless, the concept is valuable. It provides a way to visualize how smooth space-time could break down without requiring discrete blocks or rigid boundaries. From this perspective, space-time is not made of solid units. Instead, it resembles a medium in constant fluctuation, smooth on average, yet microscopically highly uncertain. The scale at which this behavior becomes significant is predicted to be near the Planck length and Planck time. At these scales, quantum energy fluctuations are strong enough to cause significant curvature variations. Space-time geometry is no longer well defined in the classical sense. This does not imply that space-time disintegrates or becomes chaotic in an observable way. The fluctuations are confined to extremely small scales, far beyond direct access. At larger scales, the fluctuations average out, producing the smooth geometry described by general relativity. This averaging process is central to understanding why classical spacetime works so well. Just as atomic thermal motion produces smooth temperature at macroscopic scales, quantum fluctuations of spacetime may produce smooth geometry when observed from a distance. The idea of quantum foam also explains why measurement becomes difficult at this scale. If space-time itself fluctuates, the notion of a fixed ruler or clock becomes problematic. Any measuring device is embedded in the same fluctuating geometry it attempts to probe. This undermines the assumption that distances and times can be defined independently of the measurement process. Instead, geometry becomes relational and context-dependent. What can be said depends on how the system is probed. Wheeler emphasized that in this environment, familiar intuitions are unreliable. Concepts such as points, trajectories, or continuous lines may no longer apply. Mathematics used to describe smooth manifolds may fail because the underlying structure cannot support it. At the same time, it is important not to overstate the significance. Quantum foam does not imply that spacetime is literally boiling or unstable in a macroscopic sense, nor does it mean that spacetime self-destructs. The effects are limited to scales where classical language no longer applies. Physically, quantum foam represents the region in which current theories overlap but do not completely agree. Quantum mechanics predicts fluctuations, while general relativity predicts that energy affects geometry. Combining these predictions suggests that geometry itself may fluctuate, but does not provide a complete description. Different approaches in quantum gravity handle this situation in various ways. Some theories predict discrete geometric structures, some predict smooth but highly fluctuating geometry, and others propose that spacetime itself emerges from more fundamental non-geometric entities. What unites these approaches is the rejection of the assumption that smooth spacetime is fundamental at all scales. Instead, smoothness emerges when fluctuations are averaged over large distances and long times. The image of quantum foam bridges the gap between abstract theory and physical intuition, allowing one to visualize spacetime not as a static stage, but as a dynamic entity subject to quantum effects. This shift in perspective is crucial. When spacetime is allowed to fluctuate, it becomes clear why attempts to quantize gravity are difficult. The object being quantized is not a field within spacetime, but spacetime itself. It also explains why classical geometry appears reliable. The foam does not disappear, but becomes irrelevant at scales where fluctuations are averaged out and the geometry is stable. In this sense, quantum foam is not a competing description of spacetime, but a candidate for what lies beneath it. Whether this picture is correct remains an open question, but its role is clear. It provides a concrete way to imagine how continuity might fail without abandoning physical reality. Spacetime in this view is neither entirely smooth nor entirely broken, but structured by scale. At large scales, it behaves as a continuous geometric entity. At the smallest scales, it may be dominated by quantum fluctuations beyond the reach of classical description. This non-smooth microscopic picture marks a shift in discussion. The focus is no longer, can spacetime be considered smooth, but rather, what replaces smoothness when it fails? Language must be careful, not because physics becomes speculative, but because current theories reach their limits. What can be stated with certainty is limited, but not trivial. Quantum fluctuations of spacetime provide a plausible reason why smooth geometry fails at small scales, yet remains accurate at large scales. They connect quantum uncertainty, gravitational response, and the emergence of classical spacetime within a single conceptual framework. This is not a final answer, but a direction. It suggests that if spacetime is quantum in nature, it is neither static nor simply discrete, but dynamic, relational, and scale-dependent. Quantum foam may not exist in future theories, but the underlying intuition likely will. The term often serves as the first image people encounter when thinking about space-time at extremely small scales, suggesting fluctuations and structure where classical physics appears smooth. Conceptually, it is useful. As a literal physical entity, it can be misleading if misunderstood. At its core, quantum foam is an attempt to describe spacetime when quantum effects become unavoidable. It arises from combining two established facts. Quantum mechanics predicts unavoidable energy fluctuations, and general relativity predicts that energy influences spacetime geometry. Taken seriously, these imply that spacetime geometry must fluctuate at sufficiently small scales. This conclusion is clear conceptually, but difficult to visualize. Humans tend to imagine space as an empty container and time as a continuous sequence. Quantum foam suggests bubbles forming and breaking inside this container, but this is not literally the case. There is no background space in which space-time foam sits. The fluctuations do not occur in space-time, they are fluctuations of space-time itself. When John Wheeler introduced the term, he did not propose a specific physical structure. He merely intended to point out a domain in which classical geometric language breaks down. Quantum foam is meant to signal the loss of smoothness and predictability, not to indicate the exact form of what replaces it. At extremely small scales, the quantities defining geometry in general relativity, distances, angles, and curvature may no longer have stable values. Instead of a single geometry, there may be a spectrum of possible geometries, each contributing according to a probability. In this sense, spacetime behaves more like a quantum system than a classical object. The term foam evokes a continuously changing pattern, rather than a fixed structure. But this is a metaphor, not a model. The metaphor is useful because it allows unfamiliar ideas to be discussed in familiar language. However, if taken too literally, it can be misleading. Quantum foam does not imply bubbles of space appearing and disappearing in a simple or observable way. It does not imply flows or oscillations detectable by instruments. It does not imply instability at scales larger than the Planck scale. If it exists, the foam is confined to scales far smaller than anything affecting ordinary physics. One way to maintain a realistic perspective is to remember that the foam is not a statement about appearance, but about calculation. When physicists attempt to describe space-time according to quantum principles, the mathematics shows that contributions from many possible geometries must be considered. The smooth geometry of general relativity emerges only as an average over these possibilities. In this sense, the foam is statistical rather than mechanical. It is not a material substance. It is a way of expressing uncertainty and fluctuation in geometry. This also explains why human intuition has limits. Intuition is built around objects moving through space over time. Quantum foam challenges both concepts simultaneously. There may be no fixed objects, no stable background, and no single timeline. Any imagery that recalls familiar physical frameworks is potentially misleading. This is why language must be careful. Saying that space-time is foamy does not mean it is chaotic in the ordinary sense. It means that classical description fails at certain scales. It also means that different theories may use the same metaphor but in different ways. In some approaches to quantum gravity, fundamental space-time is discrete. In others, it is continuous, but subject to large quantum fluctuations. Yet others propose that space-time emerges from more fundamental non-geometric entities. All of these approaches can be loosely described as related to quantum foam, but they are not identical. The metaphor only unifies them at a high level. This is where speculation appears. Quantum foam has not been observed, and there is no direct experimental evidence confirming or ruling out its existence. Its status is theoretical, inferred from attempts to reconcile quantum mechanics and gravity. This makes it a plausible idea, not an established fact. Acknowledging this is not a weakness, it is a strength. Physics advances by clearly distinguishing what is known, what is inferred, and what is unknown. What is known? Quantum fields fluctuate. What is known? Energy affects space-time geometry. What happens when these two facts are combined depends on assumptions about how quantum principles apply to space-time. This is why different theories reach different conclusions. The quantum foam metaphor also helps avoid another misunderstanding, that space-time must be entirely smooth or broken into rigid blocks. Reality may be more subtle. Space-time may lack fixed structure at small scales, without being composed of simple fundamental blocks. This intermediate situation is difficult to describe without metaphor, which is why the metaphor exists despite its limitations. Another important point: quantum foam does not imply random chaos. Quantum mechanics is probabilistic, but not arbitrary. Probabilities follow precise mathematical rules. If space-time fluctuates according to quantum mechanics, those fluctuations also obey well-defined laws, even if the outcomes are not absolutely determined. From this perspective, foam does not mean disorder, but order according to quantum probabilistic rules. That means uncertainty is constrained by physical principles, not by unstructured chaos. The value of this concept lies in how it reshapes our expectations. Instead of assuming that space-time must be smooth at all scales, it opens the possibility that smoothness is merely an emergent property. Rather than expecting a single geometry, it allows us to imagine that multiple possible geometries may contribute collectively. But once the metaphor has fulfilled its role, it must also be set aside. Progress cannot rely on imagery, but on precise mathematical frameworks. Quantum foam is only a bridge, not a destination. It is also an important reminder. Overly concrete images can create a false sense of familiarity. When we imagine space-time as bubbling or rippling, it is easy to feel that we understand something that remains fundamentally unfamiliar. But the goal here is not comfort, it is clarity. In summary, quantum foam should be understood primarily as a conceptual signal. It marks where smooth space-time begins to break down at extremely small scales. It captures the idea that geometry itself may be subject to quantum uncertainty, but it does not describe the detailed structure of space-time, nor does it claim that we can observe it directly. Keeping it in its proper role as a metaphor preserves its usefulness. Treating it as a literal picture only leads to confusion. And once that boundary is clear, attention can shift to theories that attempt to describe quantum spacetime without relying on intuitive imagery. One of the most serious efforts in this direction begins by taking general relativity exactly as it is. Rather than treating gravity as a force added onto quantum theory, this approach starts from spacetime itself and asks, what happens if quantum principles are applied directly to geometry? This line of thought is known as loop quantum gravity. The core spirit of loop quantum gravity is quite straightforward, even though the technical details are highly complex. If spacetime is truly dynamic, as general relativity asserts, and if quantum mechanics is universal, then the geometry of spacetime must also be quantized. Distances, areas, and volumes cannot vary continuously without limit, but must appear in discrete units. This approach does not attempt to unify all forces of nature. It does not introduce extra dimensions, nor does it require new particles beyond those already known. Its goal is narrower, but more focused, to describe the quantum properties of spacetime itself. Two physicists closely associated with the development of this framework are Carlo Rovelli and Lee Smolin. From the late 20th century onward, through both independent and collaborative work, they helped shape the mathematical structure of loop quantum gravity and clarified its physical interpretation. One of the most important steps in this theory is the abandonment of the idea of a fixed background spacetime. This choice brings loop quantum gravity closer in spirit to general relativity. There is no pre-existing geometry on which quantum processes take place. Instead, geometry itself is part of the quantum system. This is why loop quantum gravity is called a background-independent theory. Space-time does not exist first and then acquire quantum effects. Rather, geometry emerges from the quantum states themselves. To describe these states, the theory introduces an entirely new way of representing geometry. Instead of smooth fields defined at every point, geometry is encoded in networks composed of discrete elements called spin networks. A spin network is not a physical object inside space. It is a mathematical structure representing how areas and volumes are related. The nodes of the network correspond to fundamental units of volume. The links between nodes correspond to fundamental units of area. Together, they define a quantum state of geometry. Each link carries a quantum number, and that number determines the amount of area the link represents. One of the most notable predictions of loop quantum gravity is that geometric quantities which appear continuous, such as area and volume, may in fact take only discrete values. Each link in a spin network carries information about area. Each node carries information about volume, and these values do not vary infinitely, as in classical geometry. They appear in discrete levels, reminiscent of energy levels in atoms. From this, the theory arrives at a strong conclusion. There exists a smallest non-zero area and a smallest non-zero volume. In this sense, space is no longer something that can be subdivided indefinitely. However, this does not imply a picture of the universe built from tiny cubic blocks arranged on a rigid grid. The discreteness here is not pixel-like or based on a coordinate lattice. Geometry in loop quantum gravity is relational. Spin networks do not exist within space as objects placed inside it. Rather, the spin network itself defines space. And when many such elements combine, the underlying discrete structure becomes, at large scales, indistinguishable from a smooth continuum. In that limit, the familiar geometry of general relativity emerges as an approximation, much like fluid flow emerges from molecular motion. This point is crucial for the entire theory. Any viable approach to quantum gravity must recover classical spacetime at scales where general relativity has been tested. Loop quantum gravity is constructed so that this limit exists in principle, although a complete proof in all cases remains an ongoing area of research. Not only space, but time itself is treated differently within this framework. There is no single universal time flowing uniformly outside all physical processes. Instead, change is described relationally, Physical quantities evolve with respect to one another, not relative to an external clock. This idea directly continues a lesson already present in general relativity, that time is not an absolute background, but is intertwined with geometry and matter. Loop quantum gravity extends this intuition into the quantum domain. For this reason, the theory does not envision microscopic spacetime as a chaotic foam in the usual intuitive sense. It does not describe a wildly fluctuating geometry at all places and scales. Instead, it suggests a granular yet well-defined structure. The uncertainty lies not in geometry becoming unstable after being given, but in which spin network configuration is appropriate for describing a given situation. This is a crucial distinction. Loop quantum gravity does not claim that spacetime becomes chaotic at small scales. It claims that spacetime has a well-defined quantum structure governed by precise mathematical rules. From this foundation, several striking physical consequences begin to emerge. One of the most studied directions concerns classical singularities. In simplified models, loop quantum gravity does not allow singularities to persist as points of infinite density. Instead, it replaces them with finite, well-controlled quantum states. Rather than infinite compression, the theory suggests the existence of a transition through a minimum volume. When applied to cosmology, this idea replaces the familiar classical picture of an initial singular beginning with an alternative possibility, a quantum bounce. The universe does not begin from a singular point where all description breaks down, but contracts to an extremely small yet finite size, and then expands again. In this sense, time does not necessarily come to an end. What ends is only the classical description. Of course, the status of these results must be made clear. They are not complete solutions of the full theory, but are derived within simplified models, where key features are retained while full complexity is controlled. As such, they demonstrate consistency and potential, rather than providing final confirmation. Another important area concerns black hole physics. In loop quantum gravity, the area of a black hole's event horizon is predicted to be quantized. This opens a path toward a microscopic explanation of black hole entropy, linking geometric degrees of freedom to thermodynamic behavior. Here again, the results are suggestive rather than definitive. They indicate that the theory can reproduce known semi-classical results while shedding light on their deeper origin. However, these successes do not eliminate significant challenges. The mathematics of loop quantum gravity is extremely complex, demonstrating in full generality that discrete quantum geometry at microscopic scales always leads to smooth spacetime. At macroscopic scales remains a technically demanding problem. Connecting the theory with experiment is also difficult, since the predicted effects typically occur at scales far beyond current observational reach. There is also a more fundamental limitation. Loop quantum gravity focuses primarily on spacetime geometry and gravity. It does not automatically incorporate the other fundamental forces or the full particle content of the standard model. Whether and how these components can be naturally integrated remains an open question. Researchers in the field themselves openly acknowledge these limitations. These limitations are not regarded as failures. They are seen as signs of how fundamentally difficult the problem truly is. What makes loop quantum gravity a serious candidate does not lie in having all the answers, but in being built on clear principles. It preserves the background independence of general relativity. It applies quantization directly to geometry itself, and it produces concrete mathematical predictions that are, in principle, testable, even if they currently lie beyond experimental reach. Equally important is what the theory does not assume. It does not require extra spatial dimensions. It does not rely on symmetries that have never been observed, nor does it begin with a pre-existing space-time stage. Everything starts from the geometry already known in physics, and asks, if that geometry must obey quantum rules, how does it behave? In this sense, loop quantum gravity is conceptually conservative, yet mathematically radical. In the picture it proposes, space-time is neither perfectly smooth nor chaotically fluctuating. It is discrete, relational, and structured. Smoothness emerges only when many quantum geometric elements are considered together. It is here that the theory offers a fairly clear answer to the question, when does space-time become quantum? In this approach, space-time is always quantum in nature. What changes with scale is not whether that nature exists, but whether it is revealed or hidden by averaging. At large scales, quantum geometry appears classical. At small scales, discreteness becomes unavoidable. Loop quantum gravity does not claim to be the final answer. It presents itself as a consistent step forward, but that alone is significant. It shows that one can construct a theory in which space-time itself is quantized without abandoning the core insights of general relativity. Whether this approach is ultimately correct remains open. What it provides is a concrete example of how the smooth space-time we experience might emerge from a deeper quantum structure, and how continuity can break down without leading to inconsistency. In that sense, it becomes a benchmark against which other approaches can be compared. And then another major effort enters from a completely different starting point. Rather than quantizing space-time geometry directly, this approach asks a deeper question. Have we correctly identified the fundamental constituents of matter and forces? From this line of thought emerges what is widely known as string theory. The central premise of string theory is simple to state. The most fundamental components of nature are not point-like particles, but extremely small extended objects called strings. These strings can vibrate in many different ways, and each mode of vibration corresponds to a different particle, with its own mass and properties. In this picture, electrons, quarks, and even force-carrying particles are no longer separate fundamental entities. They are simply different vibrational states of the same underlying object. What appears as diversity at low energies becomes unity at the smallest scales. This idea developed in the late 20th century, as physicists searched for a consistent way to describe gravity within quantum principles. Earlier attempts to quantize gravity directly often ran into uncontrollable infinities. String theory offered a different path by softening interactions at extremely short distances. Point particles interact at a single location, and this sharpness leads to severe divergences in calculations. Strings, by contrast, have spatial extent, so interactions are spread out along the string rather than concentrated at a point. As a result, short-distance behavior becomes mathematically smoother. This feature turned out to be decisive. One of the most important results of string theory is that gravity is not added by hand, it emerges naturally. Certain vibrational modes of the string behave exactly like a quantum particle that mediates gravitational interaction. In other words, a quantum description of gravity arises automatically from the theory itself. This was a major motivation for pursuing this framework. For the first time, it seemed possible to have a single theoretical structure that could incorporate both quantum mechanics and gravity in a coherent way. But the ambition of string theory does not stop at gravity. Its broader goal is unification. It seeks to describe all fundamental forces and all particles within a single, consistent framework. Electromagnetism, the nuclear forces, and gravity would all arise from a common underlying dynamics. This drive toward unification has shaped a large part of theoretical physics over the past several decades. Over several decades, a large research community has explored the mathematical structure of string theory in depth, constantly engaging in dialogue with particle physics, cosmology, and even pure mathematics. The research culture of high-energy physics clearly reflects this. Ideas originating from string theory circulate continuously through conferences, research institutes, and collaborative networks associated with major experimental centers, especially those focused on particle collisions and fundamental interactions. Even though string theory itself has not yet been directly tested, its influence is clearly visible in how questions are framed and which problems are considered worth pursuing. One of the most striking features of the theory is that it requires more spatial dimensions than we directly observe. In its simplest and most consistent forms, string theory requires a total of 10 space-time dimensions, 9 spatial dimensions, and one time dimension. Some versions require even more. Almost immediately, a question arises. If these additional dimensions exist, why do we not see them? The standard answer is that they are compactified, curled up into extremely small structures, far beyond the reach of current technology. At human scales, and even at atomic scales, they remain completely invisible. A comparison is sometimes used, though it must be handled with care. A cable viewed from afar appears one-dimensional. Only upon close inspection does its circular cross-section become visible. In this way, space may contain additional dimensions that only reveal themselves at extremely small scales. But this analogy should not be pushed too far. The mathematics of compactified dimensions is far more complex, involving intricate geometric structures. Conceptually, the key point is that in string theory, space-time is far richer than the three-dimensional space of everyday experience. These extra dimensions are not optional, they are required for mathematical consistency. Without them, the theory would collapse into internal contradictions. This is both a strength and a weakness. It provides a highly constrained structure, but also pushes the theory far beyond the reach of direct experimental verification. Within this framework, space-time is not quantized in the same way as proposed by loop quantum gravity. Instead, the smoothness of space-time is preserved because the fundamental objects interacting within it are extended. Strings do not interact at sharp points like point particles. Rather, their interactions are spread out over a small region, avoiding the singular behavior typically associated with point-like interactions. In this sense, string theory approaches the problem of quantum space-time indirectly. It does not begin by discretizing geometry. Instead, it modifies how matter and forces behave at short distances, allowing space-time to remain well-behaved even at extremely small scales. This leads to a very different intuition. Space-time does not fragment into discrete pieces. Instead, it can remain continuous, while the physics within it is smoothed out at short distances. Singularities are not removed by directly quantizing geometry, but by altering the nature of what interacts within that geometry. This distinction is crucial when comparing approaches. Loop quantum gravity predicts discrete geometric quantities. String theory, by contrast, preserves smooth geometry while introducing new degrees of freedom that prevent the breakdown of the classical description. Both aim at the same problem, but start from very different assumptions. String theory also introduces a particularly powerful idea: duality. Physical descriptions that appear entirely unrelated can turn out to be mathematically equivalent. A theory defined on one space-time geometry can describe exactly the same physics as a theory defined on a completely different geometry. One of the most striking examples of this intuition is the relationship between gravity in a higher dimensional space-time and a quantum field theory defined on its boundary. From this emerges an even deeper possibility. Space-time geometry itself may not be fundamental, but instead emerges from more basic degrees of freedom that are not geometric in nature. In this view, quantities such as distance and volume may be derived rather than fundamental. For this reason, some physicists arrive at a bold conclusion: space-time itself may not be a fundamental entity in string theory. It may instead emerge from patterns of interaction at a deeper level of the theory. If this is correct, then the question, when does space-time become quantum, may be misplaced from the outset. Space-time might be only an effective concept, one that appears only when certain conditions are satisfied. Despite its rich mathematical structure, string theory faces very serious challenges. The greatest obstacle is testability. The scales at which string effects are expected to become significant lie very close to the Planck scale, far beyond the reach of current experiments, and likely beyond any that can be realistically envisioned in the near future. So far, there is no direct experimental evidence confirming the existence of strings or extra dimensions. Another difficulty lies in uniqueness. String theory does not lead to a single, well-defined universe. Instead, it allows for an enormous number of possible solutions, each corresponding to different physical constants and properties. As a result, explaining why our universe has exactly the structure we observe becomes particularly challenging. Supporters argue that this flexibility may be a feature rather than a flaw. It could reflect the true complexity of underlying physics. Critics, however, contend that without predictive power, the theory risks drifting too far from observation. This debate is ongoing, and it is precisely what makes string theory both highly influential and deeply controversial. However, in the context of quantum space-time, what matters is not whether string theory is ultimately correct, but what it demonstrates is possible. It shows that there are multiple consistent ways to approach the same problem. One path is to quantize geometry directly. Another is to modify the fundamental constituents of matter and interaction so that geometry remains smooth. String theory belongs to the latter path. In this picture, space-time does not necessarily fragment or fluctuate violently at extremely small scales. Instead, the severe infinities that plague point particle theories are softened because interactions are inherently spread over extended objects. Geometry remains continuous, but its meaning is anchored in deeper underlying structures. This significantly broadens the theoretical landscape. It shows that quantum space-time does not have a single obvious form. Different assumptions lead to different pictures, each internally consistent and rooted in established physics. In this sense, string theory does not necessarily replace other approaches. It complements them by offering a contrasting answer to the same fundamental question. How can quantum mechanics and gravity coexist without contradiction? Whether space-time becomes quantum through discreteness, emergence, or extended interactions remains unresolved. String theory suggests another possibility. Smooth space-time may persist at all scales not because it is ultimately fundamental, but because the objects within it are not point-like. This perspective does not resolve the problem, it deepens it. By opening a completely different path to quantum space-time, string theory forces the question to be posed more precisely. What actually changes when space-time becomes quantum? Is it geometry that changes, or the entities that give geometry its meaning? These questions remain open. What is clear is that string theory has profoundly reshaped how physicists think about space-time, scale, and unification. Even if it ultimately turns out not to be a direct description of nature, its influence on the search for quantum space-time is undeniable. It serves as a reminder of something essential. The path from smooth space-time to quantum reality may not be unique, and the correct description may lie deeper than geometry itself. From here, one of the most far-reaching ideas begins to emerge. Space-time itself may not be a fundamental ingredient of reality. Rather than being present from the outset, it may arise from deeper processes, much like many familiar physical quantities do. This shift is subtle, yet it changes the focus of the problem entirely. The question is no longer simply how to quantize space-time, but rather, does space-time need to be quantized at all? Does smooth geometry exist at the deepest level of reality? Or does it only appear when vast numbers of underlying degrees of freedom are considered collectively? Physics already offers many examples of such emergence. Temperature is a familiar case. It appears to be a fundamental property of matter. Objects are hot or cold. Temperature can be measured precisely, and it behaves in a stable way. But at the level of individual particles, temperature does not exist. A single atom has no temperature. Temperature emerges only when many particles interact and exchange energy. It is a collective property, not a fundamental one. Pressure is similar. It describes the force a gas exerts on the walls of a container. It can be calculated, measured, and reliably used in engineering. But pressure is not a property of a single molecule. It arises from countless collisions averaged over time. Fluid systems offer another vivid analogy. Water in a river appears smooth and continuous, and the equations of fluid dynamics describe its motion with great accuracy at large scales. Yet at smaller scales, water consists of discrete molecules moving chaotically. The smooth flow is real, but it is not fundamental. Seen in this way, emergence is not an illusion. A description can be extremely accurate, indispensable even, and still not represent the most fundamental layer of reality. What it reflects is not error, but scale dependence. And if this intuition is applied to space-time, then distance, duration, and geometry may play roles similar to temperature or pressure. They do not necessarily describe microscopic structure, but rather collective behavior. At large scales, space-time behaves smoothly and predictably. But as one moves to smaller scales, the very concept of space-time may dissolve into a deeper layer of reality. This perspective reshapes the interpretation of earlier difficulties. The incompatibility between quantum mechanics and general relativity may not arise because space-time needs to be quantized in the usual sense, but because space-time may not be the correct object to quantize in the first place. If it is an emergent entity, then the two theories may simply operate at different levels of description. Quantum mechanics governs the fundamental degrees of freedom. Space-time describes how those degrees of freedom organize at large scales. This idea appears in several modern approaches to theoretical physics, most notably in work related to the holographic principle. According to this principle, all the information contained within a region of space can be fully described by data on its boundary. The term holographic comes from the analogy with holograms, where a two-dimensional surface encodes a three-dimensional image. In physics, this suggests a deeper possibility. Volume and geometry may not be fundamental, but instead arise from a more basic description with fewer dimensions. A concrete mathematical realization of this idea was proposed by Juan Maldacena in the late 1990s. He discovered a precise correspondence between two seemingly very different types of theories. One describes gravity in a higher dimensional space-time. The other is a quantum field theory without gravity, defined in a lower dimensional setting. Remarkably, the two descriptions encode the same physics. Calculations in one can be translated into the other. Space-time geometry on one side corresponds to quantum interactions on the other. The true significance of this result lies not in its technical details, but in its conceptual implications. Space-time geometry may emerge from quantum degrees of freedom that do not themselves reside in space-time in the usual sense. In this view, distance, curvature, and even gravity are no longer starting points, but derived quantities. Within such a framework, space-time is not quantized directly. What is fundamentally quantum is a deeper underlying system, while space-time appears only when that system is described at large scales or low energies. As a result, the question, when does space-time become quantum, begins to look questionable. Perhaps space-time is never quantum in the same way that a particle is quantum. Instead, the underlying system is quantum, and space-time merely inherits its properties. If this is correct, many previously puzzling issues take on a different light. The appearance of a minimal length or minimal time may not reflect fundamental building blocks of space and time, but rather the limits of how space-time emerges. Singularities may not represent true physical infinities, but signals that the emergent description has broken down. Quantum foam, in this view, may not be literal geometric fluctuation, but a manifestation of uncertainty in the underlying degrees of freedom. Thinking in terms of emergence also helps explain why spacetime behaves classically over such a wide range of scales. Just as temperature remains smooth and stable despite arising from quantum particles, spacetime geometry may appear smooth even if its foundation is entirely quantum. This does not make spacetime any less real. Emergent phenomena are still real phenomena. Pressure can burst a container. Temperature can drive engines. Fluid flow can shape landscapes. Emergence does not deny reality, it explains how reality is organized. But every emergent description has limits. It works only as long as the conditions supporting it remain intact. When those conditions break down, the description must be replaced. For space-time, those conditions may involve scale, energy, and how the underlying degrees of freedom are organized. At everyday and astrophysical scales, space-time emerges robustly. but at extremely high densities or extremely small distances, it may no longer hold. This perspective also clarifies why no experiment has yet directly detected discreteness of spacetime or its quantum fluctuations. If spacetime is emergent, then probing what lies beneath it requires access to the underlying degrees of freedom that generate it. And those degrees of freedom may lie far beyond familiar geometric concepts, beyond the reach of current technology. What is crucial is that emergence does not reduce the need for a precise theory, quite the opposite. It demands one even more strongly. One must explain what spacetime emerges from, how it emerges, and under what conditions the emergent description remains valid. These are both technical and profound questions, and they remain unresolved. Some approaches suggest that spacetime emerges from patterns of quantum entanglement. Others propose more abstract mathematical structures. Some retain geometry as fundamental, others do not. But they share a shift in focus. Spacetime is no longer assumed to be the stage on which physics unfolds. It becomes part of the outcome. This shift also carries philosophical implications. If spacetime is emergent, then familiar notions such as locality and simultaneity may also be emergent features. The idea that events occur at definite places and times may hold only in regimes where space-time is fully formed. At deeper levels, relationships may no longer map cleanly onto spatial distance or temporal order. This does not destroy causality or physical law, it forces a reformulation. Cause and effect may still be connected, but not necessarily in ways that align with classical space-time intuition. Finally, the perspective of emergence serves as a caution. It warns that concepts successful at one scale are not automatically valid at all scales. It suggests that the breakdown of smooth space-time at extremely small distances is not a failure of physics, but a sign that we may be using the wrong variables to describe reality. From this viewpoint, the central question shifts. The issue is no longer, when does space-time become quantum, but rather, when does space-time cease to be the appropriate language? This reframing does not provide a final answer, but it transforms the entire landscape of the search. It opens the possibility that space-time, like temperature or pressure, is a powerful yet limited concept, and that possibility reshapes how the problem of quantum gravity is approached. Reconciliation may not come from forcing two seemingly incompatible frameworks to fit together, but from recognizing that they describe different layers of reality. At large scales, space-time geometry describes how matter and energy are organized. At small scales, quantum rules govern the fundamental constituents. The challenge, therefore, is not to choose one description and discard the other, but to understand how they connect. The idea of emergent spacetime offers a coherent way to think about this connection. It preserves the success of general relativity without requiring it to be universally valid in all regimes. At the same time, it respects quantum mechanics without forcing spacetime itself to behave like a particle. Whether this picture is correct remains unknown, but it provides a powerful conceptual lens. Through it, the question of quantum spacetime can be posed more precisely and with fewer assumptions. It may be that spacetime does not become quantum in the same way that matter does. It may also be that, at some point, the very concept of spacetime ceases to be the appropriate language, giving way to deeper structures that only resemble space and time when viewed from sufficiently large scales. This possibility does not diminish the reality of spacetime. It simply places it in its proper context. And once that context is recognized, broader questions about meaning, causality, and the nature of reality itself must be reconsidered while still maintaining the rigor demanded by physics. Ideas about quantum spacetime are inherently ambitious, mathematically rich, and often far removed from direct observation. This makes an unavoidable question arise. If quantum effects of spacetime only become significant at extreme scales, what can experiments actually test? And where are the limits of observation? All difficulties begin with scale. The effects of quantum spacetime are expected to become significant near the Planck length and Planck time. but these scales are far smaller than anything we can directly probe. Even the most powerful particle accelerators today remain far below the energies required to resolve such distances. This is not merely a temporary technological limitation. It reflects fundamental constraints imposed by gravity and quantum mechanics themselves. As a result, no experiment can directly observe spacetime at the scales where quantum effects are expected to dominate. There is no microscope powerful enough, and no probe capable of isolating such short time intervals without disturbing the system to the point of meaninglessness. But this does not mean that experiments have nothing to say. It means that all tests must proceed indirectly. Physics has advanced this way many times before. Atoms were accepted long before individual atoms could be imaged. Neutrinos were proposed decades before they were detected. In each case, theory did not provide immediate direct observation, but offered consequences that could be tested at accessible scales. For quantum spacetime, the same logic applies. One of the most promising observational arenas lies in gravity under extreme conditions. Gravitational waves are a particularly important example. These are distortions of spacetime itself, produced by accelerating masses such as merging black holes or neutron stars. The detection of gravitational waves by the LIGO collaboration confirmed a key prediction of general relativity. The observed signals matched theoretical models with remarkable precision. This success reinforces confidence that the classical description of spacetime works extremely well at macroscopic scales. At the same time, gravitational waves probe gravity in regimes that were previously inaccessible. Black hole mergers involve enormous energies and extremely strong curvature of spacetime. By comparing measured signals with theoretical predictions, physicists can test whether general relativity continues to hold under such conditions. So far, the answer is yes. No deviations from classical predictions have been observed, and this absence of discrepancy is itself an important result. It places strong constraints on proposed theories of quantum gravity. Any viable theory must reproduce the behavior of gravitational waves with very high accuracy. Effects large enough to significantly distort these signals have already been ruled out. This highlights an important point. Even without direct access to Planck-scale physics, experiments can still eliminate large classes of speculative ideas. The absence of anomalies is itself a form of evidence. Another potential testing ground lies in cosmology. The large-scale structure of the universe carries imprints of its very early history. Small fluctuations in the distribution of matter and radiation reflect the conditions of the early universe. Some theories of quantum spacetime predict subtle modifications in these patterns. The cosmic microwave background, for example, provides a snapshot of the universe when it was only a few 100,000 years old. Measurements of this radiation have reached extraordinary precision. They constrain how space has expanded, how matter has clustered, and how energy has been distributed. Any theory that predicts significant deviations from classical spacetime must therefore be consistent with this data. And so far, observations strongly support the standard cosmological model, based on general relativity and quantum field theory applied to matter, not to spacetime itself. Once again, this narrows the theoretical landscape. If quantum spacetime effects exist, they must be subtle enough not to significantly alter the early universe at observable scales. Laboratory experiments also play a role, though a more limited one. Precision measurements on quantum systems can be used to test whether spacetime continues to behave classically down to very small scales. Experiments using atomic clocks, interferometers, and quantum coherence have pushed tests of the relationship between quantum mechanics and relativity into conditions that appear entirely familiar. So far, both theories continue to hold with ever-increasing precision. Time dilation has been measured, even when height differences are less than a meter. Quantum superposition states have been maintained over macroscopic distances. Across all these regimes, there is no indication that classical spacetime breaks down. This places a strong constraint. If spacetime truly has an underlying granular or fluctuating structure, it must be hidden far below the scales we can currently access. Yet it is precisely here that the limits of experiment become more evident. Some proposed effects of quantum space-time are, with current technology and even with what can reasonably be imagined for the foreseeable future, effectively impossible to observe directly. Tiny geometric fluctuations at the Planck scale, if they exist, would be averaged out in any realistic measurement. Detecting them directly would require sensitivities far beyond what is allowed by limits on noise, energy, and gravity itself. This is not due to a lack of ingenuity, but because nature itself imposes boundaries, and the limitation is not only technical, there is also a conceptual boundary. If two different descriptions of quantum space-time produce exactly the same predictions at all accessible scales, no experiment can distinguish between them. In that case, their difference may lie in interpretation rather than in physics. This situation is not unfamiliar. In quantum mechanics, different mathematical formulations can describe the same observable phenomena. Physics advances not by forcing every theoretical detail to be immediately decided by experiment, but by focusing on what can actually be tested. Recognizing these limits is part of scientific maturity. In this context, the role of experiment becomes more selective. It does not provide direct images of quantum spacetime. Instead, it performs a quieter, but more decisive function. It constrains theory, requiring every new proposal to be consistent with everything already known. It eliminates ideas that conflict with observation and leaves open those that have not yet been ruled out. This balance is delicate. Theory must remain connected to experiment, but the absence of direct tests does not automatically render a line of inquiry unscientific, especially when it addresses deep inconsistencies within existing frameworks. The history of physics shows many cases where theory preceded experiment by long periods. What matters is that such theories remain grounded in established principles and, at least in principle, produce testable consequences. This is why caution is necessary. Claims that quantum space-time effects are just around the corner should be treated with appropriate skepticism. At the same time, dismissing all such work simply because it is not yet directly testable would ignore how foundational progress is often made. Experiments define the boundaries. Theory explores the interior. Within this landscape, gravitational wave astronomy, precision quantum measurements, and cosmological observations together establish a broad experimental framework. Inside this framework, space-time behaves classically with extremely high accuracy. Any quantum description, to be viable, must reproduce this behavior. Beyond that framework lies a domain of uncertainty, not because science has failed, but because the questions being asked have reached the limits of what can be measured. Understanding what experiments can and cannot test helps clarify the status of quantum spacetime. It is not an idea detached from reality. It is shaped, constrained, and guided by observation, even when its implications extend far beyond current reach. This grounding is essential. It prevents speculation from drifting into imagination. It keeps discussions of quantum spacetime anchored in physical reality, even when that reality cannot yet be fully explored. With these constraints in place, the remaining task becomes clearer: to distinguish what is known, what is unknown, and what may remain unknowable. That boundary defines the true frontier. At this point, the shape of that boundary begins to come into focus. Physics has pushed its most successful theories as far as they can reliably operate. Beyond that edge, the landscape changes not into undisciplined speculation, but into questions that current tools are not yet capable of answering. General relativity continues to provide a precise and well-tested description of space-time as a smooth geometric structure. It explains gravity, cosmic expansion, black holes, and gravitational waves with extraordinary accuracy. In every regime where it has been tested, it shows no sign of failure. Its equations remain well-behaved, and its predictions match observation. Quantum mechanics is equally successful. It describes matter, energy, and fields at small scales with unmatched precision. Its probabilistic framework underpins modern technology and all of microscopic experimental physics. Within its domain, No alternative theory has surpassed its predictive power. Each theory, when applied within its proper range, works. The boundary appears only when both are invoked at once. When gravity is weak and scales are large, quantum effects fade into the background. When quantum effects dominate and gravity can be neglected, space-time can be treated as fixed. The difficulty emerges in the narrow overlap where gravity is strong and quantum behavior cannot be ignored. This overlap defines the current frontier of physics. So far, physics does not possess a complete, experimentally confirmed theory capable of describing space-time under these conditions. Attempts exist. Some approaches treat geometry as quantized. Others treat space-time as emergent. Still, others modify the nature of fundamental objects. All are mathematically sophisticated, yet none have been confirmed. This is where current theories cease to be sufficient. They do not abruptly fail, they simply stop answering certain questions. General relativity predicts singularities but does not describe what happens at them. Quantum mechanics predicts fluctuations but does not specify how space-time responds to them. When quantum mechanics and general relativity are placed side by side, both point toward a domain in which familiar concepts begin to lose their validity. While no universally accepted replacement language yet exists, this domain is not vague. It is tightly constrained by what physics already knows. The Planck scale marks the point where quantum uncertainty, gravitational interaction, and the structure of space-time converge. Below this scale, standard notions of distance and duration lose their operational meaning. Above it, classical space-time continues to function with extraordinary effectiveness. This is not ignorance in the usual sense. It is a structured boundary embedded within physics itself. For that reason, it is essential to distinguish between what is unknown and what may be unknowable. There are questions that current theories cannot yet answer, but that future theories might. For example, whether space-time is discrete or emergent remains unknown. Whether singularities are resolved by quantum effects is also unknown. Whether space-time geometry arises from quantum entanglement or from other structures is still an open question. These are active areas of research. But there is a subtler class of questions, those that no experiment, even in principle, can decide. If two theories of quantum space-time produce identical predictions at all accessible scales, then no observation can distinguish between them. In that case, the difference may no longer belong to physical reality, but to interpretation. Physics has encountered this before. Multiple formulations of quantum mechanics describe the same observable phenomena. Choosing between them often reflects theoretical preference rather than experimental evidence. Recognizing this does not weaken physics. It clarifies its domain of validity. Some aspects of quantum spacetime may fall into this category. There may be details of microscopic structure that, even if they exist, never produce observable consequences. In such cases, physics may describe limits rather than fully reveal mechanisms. This does not mean inquiry should stop, it means expectations must become more realistic. This clarity is reflected in the research culture of quantum gravity. Researchers in this field are typically cautious in their claims. Progress is not measured by bold promises, but by internal consistency, mathematical rigor, and connection to established physics. Work continues along many directions: loop-based approaches, string-theoretic frameworks, holographic models, and numerical simulations of quantum geometry. Mathematical tools are refined, internal consistency is tested, and indirect observational signatures are sought. This effort spans universities, research institutes, and global collaborations. It is cumulative rather than explosive. Progress is often slow and technical, but this pace is not stagnation, it reflects the true depth of the problem. At the same time, there is growing recognition that further progress may require new ways of thinking, not merely extensions of existing theories. The history of physics shows that major advances often arise not by adding detail to established frameworks, but by revisiting assumptions once taken for granted. The idea of emergent spacetime is one such example. It challenges the assumption that space and time must be fundamental. Yet, with such boldness, restraint remains essential. History also shows that radical ideas endure only when they earn their place through consistency and evidence. Mathematical elegance alone is not enough. Neither is philosophical appeal. For this reason, the current boundary of physics should not be seen as a closed wall. It is better understood as a transition zone. On one side are theories repeatedly tested and confirmed. On the other are frameworks, attempting to extend them into regimes not yet accessible. This boundary is defined by scale, by measurement, and by operational meaning. It also serves an important practical function. It prevents physics from overreaching. It marks precisely where confidence ends and speculation begins. It anchors imagination to what is known. At the same time, it provides direction. By identifying where current descriptions fail, it reveals where new knowledge is needed. Singularities, the Planck limit, and the incompatibility between quantum mechanics and a dynamic space-time are not vague mysteries. They are specific points of breakdown in current frameworks. That specificity is crucial. It allows progress to be evaluated objectively. Any new theory, to be taken seriously, must recover classical space-time at large scales. It must respect quantum principles where they are already confirmed, and it must resolve, rather than obscure, known inconsistencies. Until such a theory is confirmed, the boundary remains. Yet the existence of this boundary does not diminish what physics has achieved. On the contrary, it shows how far our understanding has been pushed. Few sciences can define their limits so sharply. The boundary of present-day physics does not represent ignorance, it represents honesty. It distinguishes what can be stated with confidence, what remains open, and what may never be definitively resolved. Recognizing this boundary prepares the ground for genuine synthesis. It allows the central question to be revisited not with vague anticipation, but with clarity. What is known, what is unknown, and what may lie forever beyond determination can now each be placed in their proper context. From this vantage point, the discussion shifts. The goal is no longer to accumulate more theories, but to understand how existing intuitions fit together, where they overlap, and where they must give way to one another. This shift signals a different kind of conclusion, not a final answer, but a coherent picture of what physics can and cannot say. And after moving through all these ideas, limits, and proposals surrounding quantum space-time, the original question can finally be faced directly. Does space-time truly become quantum? Or is the question itself misleading? The honest answer is, it depends. It depends on what we mean by space-time, what we mean by quantum, and at what scale the question is being asked. At large scales, space-time behaves classically. Distances are well defined. Time orders events reliably. Geometry responds smoothly to mass and energy. General relativity describes all of this with remarkable accuracy, and no experiment has yet contradicted it. In this regime, space-time does not exhibit quantum behavior in any operational sense. At small scales, matter and energy behave according to quantum mechanics. Probability replaces certainty. Measurement disturbs what is being measured. Discreteness and uncertainty become unavoidable. This domain belongs to quantum mechanics, and its predictions have been repeatedly confirmed. The tension truly arises only when the two domains of description overlap. At small scales, matter and energy obey quantum mechanics, while space-time is typically treated as a stable background. At large scales, gravity dominates, and the geometry of general relativity works with remarkable precision. But when both gravity and quantum effects become strong at the same time, classical space-time is no longer sufficient, and standard quantum mechanics cannot be applied unchanged. It is precisely in this overlapping region that the question of quantum space-time becomes unavoidable. Different theoretical approaches answer this question in very different ways, because they begin from different assumptions about the nature of space-time itself. In loop quantum gravity, space-time is quantum at all scales. Geometry itself is quantized. Areas and volumes take discrete values, and smooth spacetime is merely an emergent approximation that appears when many quantum geometric elements are averaged together. In this view, spacetime does not become quantum at some point. It has always been quantum, while classical behavior is simply its large-scale appearance. String theory follows a different path. In that picture, spacetime remains smooth, but the objects within it are quantum and extended. Singularities are avoided not because geometry becomes discrete, but because interactions at short distances are softened. Spacetime does not fragment. Instead, its role becomes secondary to deeper underlying structures. In this sense, spacetime may not need to become quantum at all. It may remain classical, while emerging from more fundamental quantum constituents. In approaches where spacetime is considered emergent, it is not fundamental in any sense. It arises from deeper quantum degrees of freedom that do not resemble space or time at all. Geometry appears only when those degrees of freedom organize in particular ways. In this framework, asking whether spacetime becomes quantum is almost the wrong question, because what is truly quantum lies beneath it, while spacetime was never the fundamental layer to begin with. These answers are not merely differences of opinion. They reflect different definitions of spacetime itself. If spacetime is treated like a physical field, analogous to the electromagnetic field, then asking how it is quantized makes sense. If it is treated as an emergent description, then directly quantizing it may be misguided. And if it is viewed as a smooth stage stabilized by extended interactions, then discreteness may never arise. Each perspective is internally consistent. None has been experimentally confirmed, but all converge on one point. The smooth spacetime of everyday experience cannot be fundamental at all scales. Whether through quantization, emergence, or changes in the nature of fundamental objects, the classical picture ultimately fails if pushed far enough, and the determining variable is scale. At the scale of human experience, planets, and even galaxies, spacetime behaves classically. At atomic scales, it still serves as a stable background, while matter exhibits quantum behavior. Only under Planck scale conditions does the distinction between spacetime and quantum behavior begin to break down. This does not mean there exists a sharp boundary in the universe where space-time suddenly changes its nature. There is no location where geometry abruptly flips from classical to quantum. There is no single moment where such a transition occurs in an absolute sense. The change depends on resolution, not position. The same region of space can be described extremely well by classical geometry at one level of resolution, yet become inadequate at another. Just as temperature loses meaning when only a few particles remain, space-time geometry may lose meaning when too few underlying degrees of freedom are involved. For that reason, the central question must be reframed. Instead of asking when space-time becomes quantum, a more precise question is, at what scale do concepts such as distance, duration, and geometry cease to be reliable descriptions of physical reality? And in response to that question, current theory offers a clearer answer. Below the Planck scale, classical notions of spacetime begin to lose operational meaning. Distances cannot be defined without disturbing the geometry itself. Time intervals cannot be resolved without energies that undermine the very concept of duration. Even causality becomes difficult to define in familiar terms. Above that scale, spacetime continues to behave smoothly and predictably. This does not require us to conclude that spacetime is quantized in the same way as atomic energy levels. It only requires us to accept that classical spacetime is an effective description, valid within a certain domain. From this perspective, asking whether spacetime becomes quantum is somewhat like asking whether temperature becomes quantum at small scales. The answer depends on context. Temperature remains useful at large scales and fails at small ones. That failure does not mean temperature was never real, it means it was never fundamental. Space-time may occupy a similar position. This perspective also helps explain why progress in this field is slow. The question lies precisely at the boundary of what can be operationally defined. It involves entities that may never permit direct measurement or clear distinction. It requires new conceptual frameworks, not merely new calculations. This does not make the question meaningless, it makes it more subtle. And physics advances not only through answers, but by refining the questions themselves. The journey from smooth spacetime to quantum descriptions has already clarified where existing concepts remain valid and where they begin to break down. That alone is a significant achievement. So, if the question is asked directly, does space-time truly become quantum? The answer must be qualified. If the question asks whether, at sufficiently small scales, quantum principles must be used to describe space-time, then the answer is likely yes. Classical geometry cannot extend indefinitely. If the question asks whether space-time is made of discrete quantum units, the answer remains unknown and depends on the theory. And if the question asks whether space-time is a quantum object in the same sense as a particle, the answer may well be no. The most certain conclusion at present may be this: space-time, as we currently understand it, is not the final layer of reality. Its smoothness, continuity, and stability are properties valid within a certain range of scales. Beyond that range, different concepts are required. This does not diminish the reality of space-time. It simply places it in the proper context. Space-time works where it is meant to be used and fails where it is no longer the appropriate language. That is not a flaw, it is how all effective descriptions behave. And so, the question of quantum space-time ultimately settles into something quieter, but far more precise. Not when space-time becomes quantum, but when space-time ceases to be the correct language for describing reality. That realization ties everything together. It preserves the success of general relativity. It respects the necessity of quantum mechanics. It acknowledges the limits of experiment, and it does not force incompatible ideas into artificial agreement. From this standpoint, the discussion naturally shifts from debate to reflection, not vague reflection, but a careful understanding of what physics can reasonably claim. Space-time may be quantum at a fundamental level, or it may not, but what is clear is that its familiar form is constrained by scale. Recognizing this is not the end of the story, it is the condition for asking the next question correctly. Living in a universe with limits is not a failure of understanding. Those limits are what make understanding possible. At human scales, the universe still behaves in stable, predictable, and deeply familiar ways. In everyday life, smooth space-time is not a vague approximation. It is the very structure through which reality is experienced. Distances can be measured, time can be tracked, objects occupy space, events follow one another in a reliable order. At human scales, this is not a convenient assumption. It is the correct language for describing the observable world. And even if one day space-time is shown not to be fundamental, that would not make it temporary or dispensable. Temperature is not a fundamental property, yet it governs weather, biology, and chemistry. Pressure is not fundamental, yet it shapes stars and atmospheres. Smooth space-time plays a similar role. It is the correct description at the scales where human life, planetary motion, and cosmic evolution actually unfold. Physics does not aim to blindly replace every effective description with a deeper one. Its goal is to use the right description at the right scale. For that reason, recognizing limits does not weaken physics, it sharpens its purpose. The search for quantum space-time shows that even the most successful concepts have domains of validity. Space-time geometry works extraordinarily well across an immense range of scales, and only begins to fail when pushed into regimes where measurement itself becomes problematic. That failure is not something to be embarrassed by. It is a guide. It tells us where familiar ideas should no longer be extended. And from this, an important lesson in scientific humility emerges. Physics does not progress by assuming that every concept must be valid everywhere. It progresses by identifying precisely where concepts cease to apply. Knowing the boundary of a theory is as important as knowing its predictions. Smooth spacetime remains essential because it is the language used to understand gravity, motion, and causality in the observable world. No proposed theory of quantum gravity can deny that reality. If a deeper theory exists, it must recover smooth spacetime as an emergent description. Otherwise, it fails from the outset. This is where the true role of limits becomes clear. Limits are not barriers to meaning, they define meaning. When discussing fundamental physics, it is easy to assume that deeper explanations are somehow more real than effective descriptions. But that hierarchy can be misleading. Reality is organized not only by depth, but also by relevance. The smoothness of space-time is directly relevant to building bridges, navigating spacecraft, predicting eclipses, and understanding cosmic expansion. The possibility that it breaks down at inaccessible scales does not diminish its power where it remains valid. At the same time, the existence of limits prevents overconfidence. The idea that space-time may cease to have meaning at extremely small distances forces caution. It prevents us from assuming that intuitions shaped by everyday experience apply universally. It reminds us that concepts like distance and duration are tools, not absolutes. And this restraint is not pessimism, it is precision. Scientific humility does not mean retreating into vagueness. It means stating clearly what is known, what is not known, and what may never be fully expressed within familiar language. Here, the distinction between the unknown and the unknowable becomes especially important. Some questions remain open because better theories or experiments may eventually answer them, but others may never be answerable because they depend on distinctions that have no operational meaning. Accepting this does not weaken inquiry, it refines it. Living in a universe with limits also changes how we relate to uncertainty. In physics, uncertainty is often mistaken for ignorance or failure, but very often, it is the product of clarity. When physics reaches a point where a question can be posed but not yet answered within existing frameworks, uncertainty becomes the most honest response. And this kind of uncertainty is calm. It does not demand answers at any cost. It does not invent structure where no evidence supports it. It acknowledges that understanding has layers, and not every layer allows the same kind of explanation. This calmness is clearly visible in research on quantum spacetime. Theories are constructed carefully, claims are constrained, speculation is kept within the bounds of consistency with what is already known. Progress is measured by coherence, not by spectacle. This is the attitude of a mature science. That attitude also carries philosophical consequences. If space-time is emergent, then the universe is under no obligation to conform to human intuitions about continuity or locality. If space-time has limits, then reality is not required to be fully describable using the language that evolved to navigate everyday scales. Properly understood, this is not unsettling, it is liberating. It shows that physics does not fail when it encounters conceptual limits. It succeeds because it recognizes them. Not every question needs an immediate answer for understanding to deepen. Smooth spacetime remains the medium in which life unfolds. It is the stage on which meaning, causality, and experience take shape. That does not change even if spacetime emerges from a deeper layer. Emergence does not erase reality, it explains it. The universe does not become less real when its foundations are questioned. On the contrary, it becomes more precisely understood. Living with limits, therefore, does not require resignation, but an adjustment in understanding. It requires accepting that some aspects of reality are scale-dependent, and that a description valid at one level may fail at another without producing any contradiction. The history of physics has always progressed in this way. Absolute space gave way to relativity. Determinism gave way to probability. Every major turning point began with abandoning assumptions that once seemed unavoidable. The possibility that space-time is not fundamental belongs to that same trajectory. It is not an anomaly, it is a continuation. What does not change across these shifts is the role of careful reasoning, empirical grounding, and conceptual restraint. These principles do not fade at the boundary of knowledge, they become even more important. Properly understood, living in a universe with limits is not a philosophical compromise, it is a scientific achievement. It shows that physics has reached the point where it can clearly identify where understanding remains valid and where it must pause. That pause is not emptiness, It is space for reflection. Understanding that space-time works where it should work, fails where it must fail, and may not apply everywhere is not a loss. It is a form of clarity without illusion. From that vantage point, the universe appears neither completely transparent nor fundamentally unknowable. It appears as a structured, layered, and conditional reality, and that is enough. The question of quantum space-time does not require absolute certainty to be meaningful. What it requires is honesty about scale, about descriptive language, and about the reach of understanding. Within those limits, understanding remains solid even when answers are incomplete. Living in such a universe is not a problem to be solved. It is the very context in which knowledge exists. Thus, asking when space-time becomes quantum is no longer about searching for some hidden boundary in nature. It becomes a question about how description changes with scale. What is certain? At scales where measurement is possible, space-time behaves smoothly and reliably. General relativity describes gravity with extraordinary accuracy. Quantum mechanics governs matter and energy with unmatched predictive power. Each theory works exactly where it should. What remains unknown lies in the region where they overlap. At extremely small scales, concepts such as distance and duration begin to lose their familiar clarity. Whether space-time is quantized, emergent, or derived from deeper structures remains unresolved. Multiple, consistent frameworks have been developed, but none has been confirmed. And that uncertainty is not a failure. It is a sign that physics has reached the edge of what current concepts can express. Ultimately, what this question reveals is not deficiency, but restraint. It shows that nature does not promise simple answers at every scale, and that understanding does not need to be fully closed to be real. Smooth spacetime retains its full significance, because it is the correct language for the world that can be experienced. The possibility of its limits does not weaken that language. It places it in context. Seen this way, quantum space-time is less a destination to be reached than a perspective. It reminds us that reality is layered, that descriptions are conditional, and that curiosity does not have to end in closure. Sometimes, understanding lies in recognizing where to stop, and sometimes that is enough.